Earthquakes and volcanoes. Earth is the place where we live. It provides food through the farming of its soils. It provides energy resources such as oil, gas, and coal, and minerals such as gold, diamonds, uranium, and thorium. Yes, Earth also kills, even more frequently these days. Earthquakes and volcanic eruptions are the major sources. Here are two key references we used to develop these lectures. Here are some thoughts that we may have as we move around the world for studies, for businesses, and even for leisure. I am going to work in Indonesia. What is the risk that I will be killed in a volcanic eruption? I would like to attend graduate school in California. What is the chance of being killed in an earthquake? I would like to study abroad. My options are Greece and Italy. Greece has a lot of earthquakes, so is it wise to select Greece? However, my campus in Italy is very close to the very active Mount Etna. Then our left brain kicks in. By the way, what are scientists doing about these concerns? Can they really do anything? They are probably clueless, right? These scientists have gone to the moon, and now they want to go to Mars. Yet they cannot tell us a year, a month, or even a week ahead of time to leave a place before an earthquake occurs or a volcano erupts. Maybe scientists are spending their time only on so-called fundamental problems that are quite remote from our concerns. Now it is your opportunity to get a better idea of what is going on with the issues of earthquakes and volcanic eruptions. Here are examples of questions that you would like to seek the answers to as you go through these lectures. What are earthquakes and volcanic eruptions likely to occur? Are the causes, mechanisms, and effects of these natural disasters well understood? Are short-range predictions of earthquakes possible yet? Are short-term predictions of volcanic eruptions possible yet? Are proposed shielding methods from earthquakes reliable enough? Right from the onset, let's just say this. Scientists are working really hard to understand where earthquakes and volcanic eruptions are likely to occur, the causes, mechanisms, and effects of these natural disasters, short-range predictions of earthquakes and volcanic eruptions, and how to shield people from earthquakes. Our objective in these lectures is to show that significant progress has been made and that there is still a significant way to go on a number of issues. We will divide our discussion of earthquakes and volcanoes here into 6 lectures. In the first lecture, we will define earthquakes, the effects of earthquakes, and the characterization of the source of an earthquake. We will also discuss tsunamis in this lecture. In the following lectures, we will discuss volcanoes and make observations, which lead us to the tectonic plate theory. We will also discuss tectonic plate theory, including hotspot theory. We will close by summarizing the status of earthquake and volcanic prediction, the issue of shielding away from earthquakes, multiple tremor concepts, and fracking-induced earthquakes. What is an earthquake? Let's start with this basic question. An earthquake is the vibration of Earth produced by a sudden deformation of the portion of the Earth which rapidly releases energy. Energy released by an earthquake in the form of waves radiate in all directions from its source, the focus, also known as hypocenter. Highly sensitive sensors located around the world record these waves. These waves are analogous to those produced when a stone is dropped into water. Just as the impact of the stone sets the water waves in motion, an earthquake generates seismic waves that radiate throughout Earth. Earthquakes are among Earth's deadliest phenomena. Ground shaking during an earthquake can kill many thousands of people, can unleash massive ocean waves called tsunamis that can wipe out coastal cities, can liquefy solid ground and topple buildings, can cause landslides, rupture pipelines, and more. Yes, earthquakes can kill many thousands of people. Here are some examples. In the 1976 Tangshan earthquake, the number of deaths was around 750,000. It is considered to be the largest quake of the 20th century in terms of death toll. In the 1985 Mexico City earthquakes, about 10,000 people died. In the 2010 Haiti earthquake, about 230,000 people died. Let's pause and watch this short video to get a quick idea of earthquakes. Earthquakes occur in the continental crust as well as in the oceanic crust. Earthquakes in the oceanic crust can unleash massive ocean waves that can wipe out coastal cities. Some earthquakes cause upward or downward movements of the seafloor in the ocean, which in turn displaces huge amounts of seawater, creating powerful waves known as tsunamis. Earthquakes can also trigger tsunamis by unleashing underwater landslides, which also displace huge amounts of seawater. Here are examples of earthquakes and tsunamis. The largest earthquake ever recorded was the 1960 quake in Chile. It killed more than 1,600 people. with many of the deaths resulting from tsunamis. Waves reached 38 feet, or 11.5 meters, and carried debris as far as 2 miles, or 3.2 kilometers inland. The 2004 Indonesia earthquake was the third largest earthquake in the world in this century. The quake killed more than 230,000 people. Powerful tsunami waves crisscrossed the Indian Ocean and ravaged coastal regions of 12 Asian countries. The 2011 Japan earthquake killed more than 15,000 people. It triggered a giant tsunami. The tsunami also overwhelmed a nuclear reactor, creating new problems for people in the midst of destruction. Let's pause and watch this short video of the devastating effects of tsunamis. Remember that, in Japan, 96% of the population lives less than 100 kilometers from the ocean. About 50% of Earth's population lives less than 240 kilometers from the ocean. The point of these statistics is that a large number of people around the world live in coastal areas and therefore can be affected or even killed by earthquakes in the ocean via tsunamis. Hopefully you now have a better idea of how the ground shaking during an earthquake can kill many thousands of people, can unleash massive ocean waves or tsunamis that can wipe out coastal cities, and other effects of earthquakes. Besides tsunamis, other effects of earthquakes include soil liquefaction, including the toppling of buildings, landslides, floods, fires, and more. Let's start by looking at liquefaction, or how the ground shaking during an earthquake can topple buildings. Property damages attributable to earthquake vibrations depends on the intensity and duration of the vibrations, the nature of the materials used in the construction of properties, and the design of the properties. However, destruction varies considerably from one location to another, mainly due to the nature of the ground on which the structures are built. For example, Buildings on igneous rocks sustain less damage than on loose sediments or unconsolidated materials in general. In areas where unconsolidated materials are saturated with water, earthquake vibrations can generate a phenomena known as liquefaction. Under these conditions, what has been a stable soil turns into a mobile fluid that is not capable of supporting buildings or other structures. As a result, underground objects such as storage tanks and sewer lines may literally float toward the surface of their newly liquefied environment. Buildings and other structures may collapse. This picture illustrates buildings built on poorly consolidated sediments. They have tilted due to sediment liquefaction resulting from earthquakes. By the way, issues related to liquefaction of the ground are fertile areas of litigation in a number of countries. The characterization of materials upon which buildings are constructed can make or break an insurance claim. Building contractors can also be sued for knowingly building on high-risk ground, including ground with unconsolidated sediments. Here is an illustration of soil liquefaction on electricity grid. Let's now look at landslides, which is another effect of earthquakes. Earthquake shaking can cause landsliding on many scales, as some of these examples show. Basically, an earthquake can cause a slope to become unstable by the inertial loading it imposes, or by causing a loss of strength in the slope materials. Other effects of earthquakes include floods and fire. A flood is an overflow of any amount of water that reaches land. Floods may be secondary effects of earthquakes if dams are damaged. Earthquakes may cause landslips to dam rivers, which then collapse and cause floods. Earthquakes can cause fires by damaging electrical power or gas lines. In the event of water mains rupturing and a loss of pressure, it may also become difficult to stop the spread of a fire once it is started. More deaths in the 1906 San Francisco earthquake were caused by fire than by the quake itself. Damages to transportation systems such as roads, railways, airports, and more. Damage to communication systems. Economic activities in general, including agriculture, industry, and trade, are also severely affected. So, what actually causes earthquakes? That is the next question we will try to answer. Ruptures that occur along faults can cause earthquakes. We generally call these earthquakes tectonic earthquakes. Landslides, rock slides, or slumping of rocks can also cause earthquakes. We generally call these earthquakes collapse earthquakes. Movement of magma, gases, or rocks associated with volcanism cause earthquakes, which is generally termed volcanic earthquakes. Most often, but not always, movements that produce large earthquakes are usually associated with large fractures in Earth's crust, called faults. In other words, earthquakes are caused by slippage along a fault in Earth's crust. In fracture mechanics terms, earthquake is a failure along a fault zone. In other words, a fault is a surface of discontinuity which separates two contiguous rock formations. It is a consequence of a rupture which breaks out in two rock formations which were initially continuous. The word fault is commonly used in our day-to-day language. There is a fault in your reasoning. There is a fault in our security system. The meaning seems clear. However, the geologic definition is not so common. A fault is a surface of discontinuity which separates two contiguous rock formations. It is a consequence of a rupture which breaks a contiguous rock formation in two. A slip is the displacement along the fault. Faulting can be classified into three types: a strike-slip fault, a normal fault, or a thrust fault, also known as reverse faulting. The strike-slip fault has no vertical motion. One block slides sideways, that is laterally, past the other block. The fault surface is nearly vertical. The source of the Haiti earthquake, which took place on January 12, 2010, with a magnitude of 7, was a strike-slip fault. The thrust fault has a hanging wall that goes up relative to the footwall. It is due to crustal shortening and its slope is not steep. The source of the Chile earthquake, which took place on February 27, 2010, with a magnitude 8.8, was a thrust fault. The normal fault has a hanging wall that goes down relative to the footwall. It is due to crustal stretching. The source of the Nevada earthquake, which took place on December 16, 1954, with a magnitude 7.1, was a normal fault. Again, notice that tectonic stresses, which are the stresses of the area around the faults, are the orange arrows. In this slide, the strike-slip fault is a left lateral strike-slip fault. In other words, the left side block is pulling away. However, the strike-slip fault can also be a right lateral strike-slip fault. In other words, the right side block is pulling away. San Andreas is the most studied fault system in the world. Displacement occurs along the discrete segments of 100 to 200 kilometers long. Some portions exhibit slow, gradual displacement, known as fault creeps. Other segments regularly slip, producing small earthquakes. Earthquakes occur on land and close enough to the surface, often leaving visible evidence in the form of ground dislocation. The San Andreas fault is the typical example, as is illustrated here. In mechanical terms, the slips along faults associated with earthquakes are caused by the fact that tectonic stresses, or the area around the faults, have grown so high that they exceed the fault's breaking strength, resulting in a sudden release of strain energy by the Earth's crust in the form of seismic waves. In other words, the strain accumulation is more than the rocks on the fault can withstand, and the fault slips, resulting in an earthquake. This mechanism of earthquakes was first explained by H.F. Reed. Let's now describe how to locate the source of an earthquake. Seismic radiation are seismic waves which shake the ground almost everywhere. Focus, or hypocenter, is the location of the earthquake. It is the place within Earth where earthquake waves originate. Location of hypocenter is essentially an interest of science and scientists. The public is more interested on the position on the Earth's surface where the shaking associated with an earthquake is mostly felt. That location is the epicenter. So epicenter is the position on the surface of Earth directly above the focus, as illustrated in this picture. In mathematical terms, the earthquake hypocenter is at x0, y0, z0. The epicenter, which is the projection of the hypocenter on the Earth's surface, is at x0, y0, 0. The location of a focus and epicenter is determined from recordings of sensors located around the world. These sensors measure the ground motion, including those of seismic waves generated by earthquakes, volcanic eruptions, and other seismic sources. Records of seismic waves allow seismologists to map the interior of the Earth and locate and measure the size of these different sources. Nowadays, these sensors are multiple components in sense that can measure vertical as well as horizontal ground motions. In the Indian Ocean, for example, there is a dense distribution of seismic stations, and hence we have enough data to significantly improve earthquake locations. But the stations are deployed in numerous countries, and so the success of the tsunami warning system is going to rely on international cooperation and data sharing. Remember that some earthquakes cause tsunamis. So, an earthquake is a natural tsunami warning. Let's talk about the recordings of seismic waves from the perspective of estimating the epicenter. Seismic recordings are generally known as seismograms. First, waves arrive at the seismograms in the following sequence. P waves come first. They travel by compressing and stretching crust. S waves come second. They travel in an up and downward movement. Both P waves and S waves spread out from the focus in all directions through the Earth. Surface waves appear last. Surface waves move only on Earth's surface. Before we turn to the determination of epicenters, let us recall the notions of P and S waves, or body waves, and Rayleigh and Love waves, or surface waves. In addition, we will contrast P and S waves and Rayleigh and Love waves. The events associated with the arrivals of these waves are included in the seismograms that we will use to determine the epicenters. We'll start with P waves. P waves are longitudinal waves. They pass through both solids and liquids. They move forwards and backwards, and they compress and decompress. P waves are faster. P waves come first. On the other hand, S waves are transverse waves. They cannot propagate through liquids. They move in all directions from their source. S waves are slower than P waves. After P waves, S waves arrive. Now we'll move to love waves and Rayleigh waves. Love waves have displacement that is parallel to the free surface. Love waves are faster, and they cause horizontal shifting of the Earth's surface. On the other hand, Rayleigh waves, displacement is perpendicular to love waves. Rayleigh waves are slower, and the ground moves in circular motions with Rayleigh waves. Here is an illustration of an earthquake source radiating waves in all directions. These waves are recorded by seismic stations located around the world. The seismic recording here are limited to first P wave and S wave arrivals for clarity of the picture. Surface waves, or Rayleigh and love waves, travel along the outer part of Earth. Body waves, or P and S waves, travel inside solid Earth. Here is another illustration of first arrivals, which include surface waves. Because P waves travel faster, the time difference between the arrival of P waves and the arrival of S waves allows geophysicists to calculate how far away the focus is. The separation between the phases increases with distance from the focus. Using this approach, each station can be used to estimate the distance from the station to the focus. Notice that we are focusing here on the first events to arrive at a given seismic station. There are many more events arriving at a given seismic station after these first P and S events, as indicated by the ray paths in this figure. Let us now focus on the process of locating the epicenter of an earthquake by using seismic recordings. The process has 3 steps. Here are the 3 steps. The input of this process is 3 seismograms from 3 distinct locations of recording stations. First, we determine the elapsed time between the arrival of the first P wave and the first S wave for each location. Second, we determine the distance between the recording station and focus point for each station. And third, we draw a circle around each station for all the possible epicenter locations. The intercept of the 3 circles is the epicenter location, which is the output of this process. Let us reiterate. 3 station recordings are needed to locate an epicenter. At each station, we determine the time interval between the arrival of the first P wave and the first S wave, also known as SP time. Let me repeat this. At each station, we determine the time interval between the arrival of the first P wave and the first S wave, also known as SP time. A travel time graph is used to determine each station's distance to the epicenter. Here is the travel time versus distance graph. With one station, the SP time gives a distance from the station to the source. Again, note that with one station, the SP time gives a distance from the station to the source. The epicenter of the earthquake can therefore be anywhere on a circle, centered on the station and with a radius equal to the epicentral distance. With 2 stations, there are 2 circles and 2 possible locations. 3 stations allow a unique solution to the location. Note also that additional stations, 4 or more stations, are useful, as they reduce any errors, such as time pickings. Locations for epicenters can be a problem if available stations are at a similar azimuth, as illustrated here. In this case, the epicenter is much more poorly constrained. Here is an illustration of this process for 3 seismic stations located in Tokyo, San Francisco, and Sydney. The measured SP times are indicated in the seismograms. We then draw the circles to obtain the epicenter. Here is another illustration of this process, one step at a time. We have 3 seismic stations located in Akita, Busan, and Tokyo. We first estimate the time intervals between the arrival of the first P wave and the first S wave. That is, the SP times. We then use the SP times to determine each station's distance to the epicenter. When the points do not fall exactly on the line here, we have an indication that either they are variations in the crustal structure or time picking areas, not uniform VP-VS ratios. Finally, we draw 3 circles. Each circle is drawn around stations with a radius equal to the distance to the epicenter. The point where all 3 circles intersect is the earthquake epicenter, which is here, Kobe, Japan. Let's now turn to the more complex process of locating the hypocenter, or focus, of an earthquake by using seismic recordings. Again, the hypocenter, or focus, is defined by its longitude, latitude, and depth. Note that focal depth is not determined in the method we have just described. This method only determines the epicenter longitude and latitude, and the origin times. Knowing the depth of the source is important for all applications of earthquake seismology, and especially for tsunami warnings. The tsunami is generated by disturbances in the sea floor. So if the source is so deep that the disturbance of seafloor is small, then there is a greatly reduced tsunami risk. There is still a risk of a tsunami generated by a landslide triggered by the ground shaking, but the risk is smaller than for a significant seabed rupture. Therefore, it is important to know if the hypocenter is 5 kilometers or 50 kilometers deep. Unfortunately, the geometry of the stations is likely to make the depth very uncertain if we only have SP or P arrival times. The station spacing is likely to be several tens of kilometers at best, and for the Indian Ocean, at the moment, it is hundreds of kilometers in most regions. The U.S. Advanced National Seismic System has a station spacing of roughly 280 kilometers, although the coverage is far greater in high-hazard areas, like California, where there is about a 20-kilometer spacing on average. With large station intervals, the distance between the quake and the station is very insensitive to the depth of the event. When locating hypocenters with P waves only, we have 4 unknowns. the origin time, and the 3 coordinates. So with 4 or more P arrivals, this can be solved. The P arrival time has a nonlinear relationship to the location. Even in the simplest case when we assume constant velocity, therefore can only be solved numerically. The calculated travel time is here. The simplest possible relation between travel time and location is given by this formula. We can find location by minimizing the sum of the differences between observed p-wave travel times and calculated p-wave travel times. This distance can be measured using least squares. The squaring makes the solution very sensitive to outliers. So algorithms normally leave out points with large residuals. We've now concluded our discussion of what earthquakes are and the descriptions of methods for determining epicenters and hypocenters. When we return, we will describe the methods for determining the magnitude of earthquakes, the source mechanism of earthquakes, and tsunamis.